Okay, we are going to start with this lesson today is on the sun. Okay, welcome everyone to class, and we are going to do the lesson on the sun. All right, and hey, as you know, the sun is the center of our solar system. That is very, very obvious. And many times, the question is, how big is the sun? This is a little picture that I found very interesting that shows kind of the sun in perspective to the Earth. All right, so that little green dot would be the size of the Earth. Imagine how massive and big is the sun, that one of these small flares of the sun, that is actually thousands of kilometers into space, and is much larger than the Earth. I've read in one website that you could put 109 of these little dots in line across the diameter of the sun. Okay, and if this dot were a sphere, you would be able to put 1,000,000 Earths, over 1,000,000 Earths within the volume of the sun. Okay, but the sun is really all a huge ball of gases. As we were talking before, when we were talking about the nebulas and how these are large areas of gas that they start collapsing together with a gravitational force, as these massive balls of gas start collapsing together and getting closer and closer together, they form stars. All right, so the star forms when the amount of gas is so huge, so closely packed together, that it starts a process of nuclear fusion in the core of the star. Okay, so here we have a diagram of the different layers of the sun, and let me grab the pen. So right at the center we have the core, and this is all of this volume is really not gas. Okay, it's not liquid, it's not solid, it's the fourth state of matter. Okay, do you know what is the fourth state of matter? What is it called? Okay, what is the fourth state of matter? So we have that the regular states of matter that we know are liquid, solid, and gas. But there is actually another state of matter, and it is called plasma. Have you heard of that? Okay. So plasma is actually when gases get ionized. All right, so an ion of an element is when the temperature, the energy of that element is so high that the electrons, instead of staying close together to the atom of the element, they start to move freely around. Okay. All right, excellent, Alec and Natalie. So yes, plasma is the fourth state of matter, and because most of all the material within a star is in a plasma state. Okay, plasma is the most common state of matter in the universe. All right, so even though here on the Earth, even though there wasn't anything here on the Earth, there's very little on the Earth that is in plasma state, the most common thing in the universe is elements in a plasma state. So Okay. Yeah. Some, I don't know. All right. The center of the sun is also plasma. It's very, very dense, okay, plasma, but it's still in a plasma state. And the reason for that is that it's so compacted that it's very, very hot. So we are talking about in the core, the temperatures reach about 15 million Kelvin. Okay, 15 million Kelvin. Kelvin is the absolute temperature, okay? So it's the absolute scale of temperature that starts at minus, 370 something centigrades, okay? But it's very, very hot, all right? So the hottest area in the sun is here at the core, okay? Then away from the core, you have the radiative zone, okay? And then you have outside of that the convection zone. The next layer is called the photosphere. That is actually the layer of the sun that we see, okay? The chromosphere is an area that has different colors. And then the corona is kind of the surface of the sun normally is what we see as the photosphere, okay? That is the lighted, illuminated area of the sun. And the corona is emissions of rays that go away from the sun for, thousands of miles from the sun, okay? And is very, very large. So those are the layers that we have on the sun. And in the lesson, I put links to articles about each one of these. So let me see. Let me go to Safari, come on. Where was I had all the things open here. Don't tell me that they were closed. I hope not. Okay, there we go. So let me go to the lesson for today, and I'll show you what are some of the things that I had there linked. So we are on lesson 6, our star, the sun. And here we have a link to the presentation that I have, an article on the sun, and some videos about the sun and solar weather that are very interesting. Okay. There's also a couple of other links, all right. And there's a link here about plasma, all right, that talks about what plasma is and so on. And so let me go here to the article on the sun itself. Let's see what we have here. So most of the sun is composed of hydrogen, okay, and helium, all right. So 3/4 of the mass of the sun is hydrogen, all right, and that is the thing that is being fused all the time into helium, okay. And we are going to learn about that process pretty soon. Let me see what is the next one. Okay, so here this other graphic of the layers of the sun have information about the temperatures that are at the core. Okay, so 14.5 million Kelvin, and that is the area where the thermonuclear reactions occur. Then the radiative zone is an area where the radiation of energy keeps traveling around and around in this zone for thousands of years until it reaches the convective zone. Okay, so the radiative zone is 2 million Kelvin, all right, so significantly lower in temperature. and the temperature here is low enough that there is no more thermonuclear reactions possible. In the convection zone, the temperature decreases rapidly from the 2 million Kelvin to the temperature at the top of the photosphere, that is 6,000 Kelvin. So that is the temperature right here at the surface of the sun. And here, because of the difference in temperature, the material, the gases, the plasma, okay, in this area of the sun, moves in a convection zone. Okay, so the cooler material sinks. As it sinks, it heats up and then it rises up again. And as you can see in this graph, there are several different convections that happen. Have you ever boiled, like something dense like oatmeal or sauce, tomato sauce, and so on? You can see when you do that things kind of bubble up, all right, and they explode up, and so on. That is kind of the movement of things that happen through convection, where the bottom of the pan is hotter than the top, and so the liquid, whatever it is that you are boiling, moves in a convection movement. Okay. These graphs show the sun kind of reddish, and the surface. This one also shows it kind of reddish, yellowish, and so on. But in reality, the photosphere is absolutely white. Okay, so the light that comes from the sun is actually very, is very complete, if you wish, in the spectrum of light, and is white. We see the sun yellow because of the same reason of why we see the sky blue. Remember last time in the class we were talking? That's a motivational speech. Okay, we need to have someone. Okay, I'm going to mute everyone else. Okay, all right. Yes, so in the convection zone, you have the same movement of material as in the mantle of the Earth. That is a good point. That is a lot more rapid, if you wish, because the material in the mantle is a solid, so we are talking about rocks and liquids, so we are not talking about plasma. In the sun, you have that all this material is plasma, which again is ionized gases. And the density of this area is actually, if I remember correctly, is less dense than the atmosphere. Okay, so it's less dense than the air that we have. Even the density here at the core of the sun is extremely high, but as it moves away, the gases, the plasma, is a lot less dense. In the corona, and outside of the surface of the sun, the atmosphere of the sun is a lot less dense. All right. Okay. If you have any questions, just remember to type them in the chat. Okay. The sun has also very interesting magnetic fields. You know how the Earth has kind of a very consistent magnetic field with a North Pole and a South Pole right at the poles of the Earth, and then it makes a consistent magnetic field that envelops the Earth, and that is actually a very good thing. The reason why the Earth has a consistent magnetic field is because the magnetic field of the Earth is generated by the rotational movement of the core of the Earth that is made mostly of iron, okay? But it's just one movement, all right? So that one movement of the core of the Earth generates one huge magnetic field around the Earth. In the sun, because the convection happens in the convective zone in a turbulent manner, that the magnetic fields are very, very chaotic, and they are constantly changing, and there are thousands of different magnetic fields. And these magnetic fields are what cause the plasma kind of to move in this type of arches or filaments and then flare up into space. Okay? The sun also turns, all right? So it actually turns it takes for the equator of the sun, the plasma at the equator of the sun, it turns in about 25 days. The plasma at the poles of the sun take about 30 days. And that differential in rotation also causes the different magnetic fields to be generated, because you don't have all the plasma rotating at the same speed all together like it does on the Earth, and creates a consistent magnetic field. Here in the sun, you have a very, very chaotic magnetic fields that form into loops and many different things. Okay, so that is, I think, very interesting. Okay, let's see. Now we are going to talk about nuclear fusion and the reaction that actually happens at the center of the sun. Okay, I really want you to be able to understand this discussion. So if you do have questions, or if you don't understand something that I'm saying, please write that in the chat. Okay, so like I mentioned, most of the gas in the sun is hydrogen. Okay, hydrogen is composed of one proton. All right, so one proton, the protons have a positive charge. All right, so we are going to write here that the ones that are in red, the protons, have a positive charge. All right, the electrons around the protons are kind of irrelevant here, because again, this is a plasma. So what happens with the plasma? Where is the electron of this hydrogen atom? Is it close by? What was the difference between a hydrogen gas and hydrogen plasma? Type your answer in the chat. Anyone listening? Anyone thinking? Okay. Are you here? The electron is hiding? No. So, where another answer? What is the difference between the gas, okay, and the plasma? All right, so let me explain. So if we were to draw an atom of hydrogen gas, you would have the proton, okay, and the electron would be orbiting around the proton, okay. So the gas has the electron orbiting okay. So the plasma is the state of matter, all right. So it's actually how matter is. So if this were gas, the electron for this atom of hydrogen would be here around this proton, and the electron for this atom of hydrogen would be also flying around the atom. When you have when you heat up the gas, the electrons start getting so much energy that they start flying all over the place, okay. So the electrons is not anymore interacting with this single proton in the plasma state, and the proton is an hydrogen ion, Okay, let me write that here. The word is ion. So an ion is when you have, I wish I could type better. Here, let's see, it's there. No, I cannot do so. ION. so, so an ion is when the element loses some of its electrons because they are overly energized and they are flying loosely within the vicinity of the element. Okay, so that is why in this case we are not drawing the electrons, because the electrons are just flying all over freely, moving freely. That is what makes plasma. All right. Here on the Earth, we can see plasma mainly in lightning. Okay, so when you see a lightning bolt, is actually the gas of the atmosphere that gets electrified, okay, and turns into plasma. All right, so imagine again, there's so much energy, the electrons are traveling freely so fast that they turn the gas around the lightning bolt into plasma state. That is what makes the lightning. Okay, so when you see a lightning bolt, you are seeing plasma, gas turn into plasma. All right. I haven't had the opportunity to see the aurora on the northern sky or the southern sky, but the aurora borealis or the aurora australis is also plasma, okay, that in the upper atmosphere, the gases get also energized and they turn into plasma, and so that is where they start glowing. All right. So another place where we see plasma, let me check this. I think I had one of the websites here. Okay, so here we see that in the aurora you see plasma. Okay, in the lightning bulbs, also the neon lights, all right, have plasma inside the tubes. So those tubes are filled out with gases, and when they get electrified, the gases turn into plasma. All right, the different colors are because of the different gases inside the plasma tube. Does that make sense? Okay, so the same thing happens in the sun, that it is all plasma. Okay. Sam is asking, could we simulate a mini sun here on Earth? All right. And the answer is actually no. We are trying. Okay. Scientists are basically trying in order to create nuclear fusion reactions in a controlled manner. Okay. The only type of nuclear fusion reaction that we have been able to do is in the hydrogen bomb, where this reaction that is described here happens, but it's very destructive, so it's not controlled. All right, so nuclear fusion is very difficult to achieve because of the following. Okay, so now we know that this hydrogen is an ion. Okay, so we only have the protons. The electrons are just flying freely all over the place. Now, the protons in the core of the sun are so highly energized because of the pressure and the temperature. Remember, 15 million Kelvin degrees of temperature, that these photons, they collide. Sometimes they collide so hard together that they fuse into one atom. Okay, so now the protons have a positive charge. Both of these protons have a positive charge. All right, what do you know about electromagnetism? You know, magnets. What happens when two magnets of the same polarity, when you try to push them together? What happens if you try to push two magnets of the same polarity and you try to push them together? That's correct. They reject each other. Good job, Macy. All right. So they won't go together. And so that is what normally happens here with the protons. These protons don't want to stay together, okay? Because they are the same charge. So when they collide, if they don't come with enough energy, they are going to repulse each other, you know, because of the electromagnetic force, and they are going to be separated, all right? However, in the core of the sun, the electrons smash with so much force together that for a small instant they are so close together that there's another force, okay, called the strong nuclear force. I'm going to write it here in the chat. Strong nuclear force that is stronger than the repulsive force of electromagnetism. The strong nuclear force is extremely strong, is very, very strong, and is what holds the nucleus together. All right, because imagine, if it were for electromagnetism, you wouldn't have any elements other than hydrogen. Okay, but Heavenly Father basically created this strong nuclear force in order to keep these elements together. All right, but the strong nuclear force only happens if the two nucleons, the protons or the neutrons, are very, very close together. All right, so it doesn't happen at large distance. So if they are not energized enough, the protons would come and the electromagnetic force will repulse them before they touch. Okay, but if they come very fast and they collide, and then the strong nuclear force takes over, then they are going to fuse. Okay, in this moment of fusion, one of the protons expels a positron, which is the positive charge, and turns that proton into a neutron. All right, no charge. And then it ejects a neutrino, that is a particle, very, very small, but with a lot of energy. Okay, and the neutrinos go just flying out. They are very, very small. They go through everything. So here we have now that out of two atoms of hydrogen, we created one atom of deuterium. Okay, deuterium is kind of an unstable element that only happens inside the sun. All right, because again, this is when the two protons fuse together. Then this deuterium, I'm going to write it also here. Deuterium means two nucleons, okay? So you know how the book in the Bible, Deuteronomy, okay? Deuteronomy means second accounting or second counting of the law, all right? So that comes from the Greek. So here that is where you have also deuterium, meaning two nucleons put together. If this atom of deuterium collides with another atom of in French, you know, deux also means two in French, and that is also coming from Greek. Okay, like a lot of these words. So if the deuterium collides again very fast and very close with another a proton of hydrogen, then is going to fuse again and is going to form a helium atom now of tritium. Okay, tritium means 3. And the energy differential is going to be expelled into a gamma ray. This gamma ray is the part, okay, of the reaction that gives out most of the energy, all right? And this gamma ray is going to start traveling at a random direction out of the core into the radiative zone, okay, for thousands of years, and then eventually it will be able to escape. And when it gets into the photosphere, onto the surface of the sun, the gamma ray explodes, if you wish, into photons. And that is the light of the sun, the sunlight that we receive on Earth. So the sunlight of the Earth is generated at the core from this nuclear reaction, okay? And it comes off that way. When you have 2 atoms of tritium colliding together, then they are going to generate 2 atoms of hydrogen, 2 protons, okay, of hydrogen, and 1 atom of helium. This one is now in a stable state. Helium-4, 2 protons, 2 neutrons, okay, and everything is going to be done, okay. Is what is happening in the nuclear power sub or a carrier similar to what is happening in the sun, just with uranium? So, excellent question. So, this reaction is called nuclear fusion. Nuclear fusion is when you put things together, you fuse them together. So you start with light elements and end up with a heavier element. In the nuclear reactors, like you have in a nuclear power submarine or a nuclear plant, the reaction is called fission, nuclear fission, okay? And nuclear fission is the opposite reaction, is when you separate, okay, heavy elements into lighter ones. Okay, so fission is you are actually separating, you are dividing these heavy elements, and that is why nuclear fission reactions need uranium. Uranium is a very heavy element, okay, and so what they do is they in order to make this fusion, this fission possible, they need to enrich the uranium to make it with more protons than normal, okay? And then when that heavy uranium is bombarded, okay, with energy, they divide and separate into plutonium, which is lighter. And in that separation, when the nucleus separates, remember what holds the nucleus together? What force is it that we talk about that holds the nucleus of an atom together? What was it? Anyone remember? Your microphones are on, so you can talk or you can chat. What was the name of the force that holds the nucleus together? Yeah, nuclear force, but it has a special name because there's 2. It's called the strong nuclear force. Okay? So
I wasn't getting there.
So the strong nuclear force is what holds the nucleus together, and when you make the nuclear fission reaction that separates the nucleus into two, the liberation of that strong nuclear force is what causes the energy of nuclear fission. And so a submarine or a nuclear power plant is powered that way. Okay? In reality, okay, in practice, what happens is that these gamma rays that are expelled out of the nuclear fusion reaction generate energy, but each one of these gamma rays is not that much. What makes the incredible amount of energy of the sun is the number of these reactions that happen every second. So when you total all the reactions, all these gamma rays and everything in total, then you have a huge, huge powerhouse, okay? That is where the energy of the sun comes from. So the sun is constantly converting, transforming hydrogen into helium. So see that we start with 4 atoms of hydrogen, and we end up with 2 atoms of hydrogen and 1 of helium. Okay? And so that is, we started actually with 6. So we have these 6 atoms of hydrogen, okay? These 6 ones together, all right? And then we end up with these 2 of hydrogen and 1 helium. So in every chain of reaction of this type, you have that 4 atoms, 4 ions of hydrogen get transformed into 1 ion of helium. All right. These other 2 will participate in another reaction just like this at some other moment. All right. So that is the reaction that happens in the sun all the time. So let me see, I have so here is an article that is called the proton-proton chain reaction that explains exactly this same reaction. Okay, and there's the article here at the solar core. It says that, okay, 3.6 times 10 to the 38 protons, okay, of hydrogen nuclei are converting into helium every second. Okay, so this is the amount of energy, of joules, that is produced every second in the sun. Each one of the reactions is not that big, but as you put them all together, it is really, really big. So someone was asking if we can make, let's see, someone was asking, could we make something like the sun? Okay, could we simulate a mini sun here on Earth? The problem that we have is that we don't have the mass of the sun. We cannot reach the temperatures at the core of the sun to sustain a nuclear fusion reaction like the sun does. All right, you probably wouldn't want to get that hot, and the energy that it takes to accelerate 2 protons fast enough to make them collide with the same energy and speed as they do in the center of the sun, the energy that it takes to accelerate those protons is more than the energy that you obtain out of the reaction. Okay, so it's not economical, if you wish. Okay, so we haven't been able to figure out how to do a nuclear fusion productively here on Earth. All right, so that is what happens at the center of the sun and how the energy of the sun is produced. Okay, and this energy travels through space, and in fact all the solar system is enveloped, okay, with this energy from the sun. Of course that it gets kind of diffuse after a while, okay, because the solar system is so large and everything, but still it influences a long ways away. Okay, so all the planets in the solar system feel this energy as it's dispersed, okay, through the solar system, and it's called the heliospheric current sheet. All right, so this is kind of in this shape, and is basically, this is a representation of the plasma, the energy that is moving from the sun around the solar system. Okay, so the sun goes into cycles where there are, over every 11 years there's more activity on the surface of the sun, and so that activity produces more solar flares, and then it goes down into less activity. That these solar flares causes ejections of material onto space. That is called a solar flare or a coronal mass ejection, when it's actually, if it's a solar flare, it's just a lot of light energy. A lot of these gamma rays get liberated and transformed into photons at the same time. If it's a coronal mass ejection, it is actually a burst of plasma that gets spewed into space. All right. Here we can see how the plasma on the surface of the sun gets arranged into different filaments following the magnetic fields. And as, like I was explaining earlier, the magnetic fields in the sun are very convoluted and chaotic. They are not like the ones on the Earth. And if one of these coronal mass ejections or solar flares comes directly towards the Earth and hits the Earth, the magnetic field, the magnetosphere, which is the magnetic field around the Earth, is what protects the Earth from that plasma going through and hitting us. Okay, so imagine that if this large amount of plasma, which is highly energized gas, ionized gas, were able to actually hit the Earth and go through the atmosphere and hit us, you would get probably a huge sunburn at least. Or, you know, at the minimum, you would get all the electric circuits and materials basically burn, you know. So not a very pleasant thing to see. But thanks to the magnetosphere, the sphere that covers the Earth, when these plasma rays come, the magnetosphere diffuses the plasma and sends it around the Earth so it doesn't penetrate. The only thing that kind of gets into is the plasma sometimes concentrates on the poles, and that is what generates the auroras. So the northern lights, exactly. So that is the plasma from the sun concentrated around the poles on the top of the magnetosphere, where the magnetosphere kind of comes together onto the poles of the magnet of the Earth. But think about it, if our magnetic field were chaotic like the sun's, then the Earth would not have much protection. All right, so here we can see again how amazing Heavenly Father created our Earth, that created it with a magnetic field that protects us from the sun and lets the rays of the sun come in at exactly the right amount to let us have life here on Earth. All right. If we were bombarded either with, not all the planets have a magnetic field, because if you don't have a core that is rotating inside, an iron core that rotates, it would not generate a magnetic field. So not every planet has a magnetosphere. If you don't have that, then the sun, the rays of the sun would go through unimpeded, and it would probably hit the surface of the planet so much that it would evaporate all the water and blow the atmosphere out. Okay, so I find that to be amazing and beautiful, really. Exactly like in Mars. Mars doesn't have an atmosphere because it doesn't have enough mass, and it doesn't have a magnetosphere. It doesn't have the things needed to protect it from the sun. Okay, so in the lesson there is a quote from this talk from Elder Neil Maxwell. He was one of the 12 apostles. I don't know if you remember him, but I remember him very well. And this is a talk that he gave at BYU in one of the devotionals at BYU. And it's called All Hell is Moved. And in one part of this talk, Elder Maxwell compares the light of the sun. I wasn't able to find it exactly here, but it compares the light of the sun to Jesus Christ, to the Son of God. Okay, and let me see if I can find it. Okay, let's see there. Okay, so it has here, the fiery sphere we call the sun, which guides our solar system, will one day burn out. It's going to take, billions of years. Okay, scientists estimate that our sun is about halfway in the process of having converted all the hydrogen into helium. Okay, so we are about halfway from that main sequence process. Okay, so the fiery sphere we call the sun, which guides our solar system, will one day burn out. But it provides us with a useful analogy. We may cover our eyes or turn from its light, but its light is still there. We may see it through glass darkly, but it glows on just as brightly. For a few hours we call night, it seems to be gone, but it is still shining there and will reappear on the morrow. Storms may darken the sky at noonday, but the sun is still there and will soon break through. So it is with the Son of God, about whom this choir has sung so well today. We may turn from him, but he is still there. We may feel that he is hidden from us because of the cloud cover of our concerns, but he is still close to us. We, not he, let something come between us, but no lasting eclipse need ensue. Our provincialism cannot withstand his universalism. Our disregard of him is no match for his love of us. Yes, Jesus of Nazareth lived, he lives now, he guides his church. So what is the similitude here that Elder Maxwell draws between the Son and the Son of God? What is the similitude between the two? If you want to talk, you can unmute your microphone. I'm going to do that. Okay. What is the similitude between the Son and Jesus Christ, the Son of God? Go ahead. You can talk or you can type your answer. So the question is, what is the similitude between the Son and the Son of God? Both are bright beacons in a way. The Son gives us physical life. The Son, Jesus Christ, gives us spiritual life. He also gives us life eternal. Yeah.
And they're the light and the life of the world.
Jesus Christ is the light and the life of the world. Yes.
And the sun is the light of the world.
Yes, and the sun is the light of our world here physically. Okay. Without them, we wouldn't be able to live. That's right. They are both the center of our lives, or should be the center of our lives. That's cool. Yeah. They both provide for our needs. It doesn't matter whether we want their influence or not, they are always there. Isn't that something? You know, we can cover from the sun, we can get inside, not, try not to pay attention. But it's interesting that the sun is still always there. Let me read this one. Yeah. So it says a little. I heard that on the dark side of the moon is reflective, and if dark side of the moon was facing the earth, it wouldn't get dark at night. It would be as if the sun was always on. I don't know. I don't exactly understand that. We have a lesson coming up. Let me see. Okay. We have a lesson coming up that we are going to talk about the moon. All right, so actually, yeah, a few lessons about the moon. And we are going to talk more about the why, how the moon moves and everything, and why it always faces us, what is the dark side of the moon, and so on. Okay. Did anyone get up early enough to see the eclipse this morning. So today at around 5 in the morning here in Utah time, we had a total lunar eclipse. Yes, it was really awesome. Yes.
Could you see it in Texas?
Yes, you could also see it in Texas. Yeah, it was actually visible. Yes. So it was really, really interesting. So the entire surface of the moon, the light was like colored rock. Okay. This was actually the reflection, if you wish, of the sun around the Earth atmosphere, and so it gave it kind of a reddish color. So, Nicola, you said that you saw it as a seminary class. Okay. I think that you could also see it in Bolivia.
It was really cool.
Yes, it was really cool. Oh, so you said that it was rainy and cloudy in Tennessee, so you couldn't see it. I'm sorry.
Yeah.
Bummer. That is always my fear. Here in Utah, it was actually a very clear night, and you could see it very, very well. And you saw it in Ohio. Excellent. All right. So this was a very unique event. Actually, there's going to be two other lunar eclipses, okay, coming up next year. So that is kind of unusual. We are going to have a sequence of 4 total lunar eclipses within very short period of time. Okay, so I'm going to let you know when the next one is, so we can make sure that we can see it if there's no rain cloud cover or anything like that. All right. Okay, so this was our lesson on the sun. Okay, the assignments that you have after studying the things that I have there. Okay, I have some questions for you to think about and reason and relate. What would happen if there were no sun? How does the Earth protect itself from solar weather? What are the beneficial things that we get from the sun? And what are the beneficial things we get from Jesus Christ? All right, and then I have a couple of assignments that you could do. One is an activity. Describe the different layers of the sun and what happens in each layer. And the other assignment, teach a family home evening lesson comparing the light and warmth of the sun with the light and knowledge we get from Jesus Christ. Use the scriptures to teach about the light of Christ and how it affects us. All right, so those are the assignments that we have. So let's finish with a word of prayer. I'm going to stop the recording. Thank you very much for joining.